Thank you very much. So yeah, I'm excited to talk to you today about this Mercury project, which is one of a few feature processing tools we have at Wayfair. It was built with a specific set of use cases in mind by, a number of folks pitched in, but it was kind of on average about a 2 to 3 person kind of project that found a lot of success. It does some unusual things that I want to tell you about today. So the core idea behind Mercury is it's a very opinionated feature processing platform, specifically designed around lowering the effort to define features, similar features, and to lower the compute resources necessary to calculate them. In the long run, the goal of this project is to improve ML performance because small teams can effectively manage more ML signals and therefore have their models have access to more features to learn from. This is achieved because at its core, Mercury assumes you aren't writing a single feature at a time. Rather, what you're doing is writing, building, and consuming features as a group together. Features can be as few as, say, 6, or they can be significantly more, over 1,000. So maybe it's helpful to illustrate this with an example. Let's say you're trying to figure out how popular a product is going to be with customers. If you're working in such a problem space, it's not uncommon to have similar features like the two that I'm showing you here. You can count the number of times the product has been ordered on, let's say, different browser experiences and over different time windows. And Mercury treats this not as just some accident, rather it's a core design concept for us. Mercury kind of nudges you to define and build these features together. And I'll describe this how later. But before I do that, what I actually want to discuss is a general framework for trade-offs in machine learning systems that'll help you both understand the decisions we made with Mercury, and I think it'll be hopefully applicable to some of the ML applications you may work with. So at its core, this is a conversation around trade-offs. So if you take any production enterprise ML system, you can collect its characteristics into like 3 main groups here. In generally, we face trade-offs between these 3 axes. So the first of these is predictive performance at some business critical task. Many widely used statistical metrics for this, F1, NDCG, but also many business metrics can also be thought of as falling under this category. Then you have resource efficiency, that's the number of CPUs, GPUs, cloud costs, or maybe it's hitting your latency budget. And lastly, there's the human effort needed to maintain and evolve the system. You can measure that in things like headcount, hours spent, velocity, things like that. So a core theme of this talk is that we should be deliberate about the path we want to take through this 3-dimensional space. So in that vein, I'd like you to think about the following example. Here, I'm showing you 2 models. One's in red, one's in purple. The red one's more predictive, but it's also more computationally expensive. It's more operationally complex to maintain. So which one of these would you deploy? Which one when faced with this trade-off the last time you had this at your company, which one did you favor? So in general, there's no single answer to this question. It depends on all kinds of things. It depends on, can your team handle supporting the more complex system? Do you need something simpler? Can you move your resource budget, or is it fixed? Maybe you don't have a way to get more VRAM, or you can't move your latency budget. And I think another question is, how valuable is this business problem to your company? What I want to emphasize is that a big driver in all of this is opportunity cost. What else could a team be working on? Here, it's helpful to introduce this framework of like tall and wide teams. Tall teams kind of tend to iterate in the same problem space over time and incrementally improve a core function. Wide teams tend to kind of build something good enough and then move on to a net new problem that maybe hasn't been covered by ML before. And, it's not always clear that the needs of those 2 team types are going to be exactly the same. What I want to emphasize here is that company context can determine where we prefer our ML systems to be in this 3-dimensional space. It's not often about making a single model maximally predictive, rather than it is about optimizing the portfolio of ML systems a team can effectively support, whether that's a few or many. Now, within this concept of trade-offs, I think it's important that we talk about the flexibility of our feature platform. So specifically, I want to talk about how much flexibility users should have in defining the features that they use. Should they be able to build anything in any way? Or should there be strict guidelines for how features are produced and consumed? At first, it's very tempting to think everything should be permitted. How can we know ahead of time what some ML practitioner might need to do to deliver business value? But At the same time, if everything is permitted, it's harder to provide operational guarantees at platform level for the features and the ML systems. A more restrictive approach is often easier to maintain and better out of the box. So both of these approaches have merits, but I personally strongly suspect that on average, like across our industry, we probably overvalue flexibility a little bit because it's easier to kind of envision this hypothetical best case performance we can get through flexibility. But we have a harder time thinking about the like longer term maintenance and overhead and opportunity cost that we get from increased flexibility. So the reason I think flexibility comes at a high cost is that every ML practitioner you know is always short on time. There are too many experiments to run, there's too many features to write, there's too many projects you could be working on, and you don't ever get to put into practice all of the flexibility you might be given to you. So another way to say this is that teams have bounded time. They're not always trying to perfect a single model. They're looking to maximize the total value of a portfolio of projects. And we can think of this in terms of a team having like a carrying capacity, a total amount of things that they can support, rather than just focusing on the velocity to ship one thing. So down at the bottom, I want to show you the approach we've taken, which is to first make features more efficient and maintainable to produce, get a lot of them. And then over time, as you have access to more and more signals, models can become more predictive out of the box. So the way Mercury makes features more maintainable is to reuse the recipe and pipeline for similar features. And the key idea here is that related features can be thought of as, kind of filling in the blanks on a common pattern. I've shown two examples of this in these gray boxes. You can quickly see from the one in the top that, yeah, you can be filtering by different browsers or aggregating over different time windows. And through those combinations, you quickly get a lot of leverage. It's easy to imagine being able to get dozens more from the pattern I've shown you. And for completeness, there's another example below that. So in preparing this talk, and as you've kind of heard from others, you've heard multiple people use the term feature group. I think it's a widely appealing phrase, but is one that's a little bit overloaded. So I want to follow suit here and be very specific about my definition that I'm using here. When Mercury talks about a feature group, we're thinking about two core things. One is you're sharing the same template pattern here. The second is that you're sharing the same source event. So there's that allows you to basically build the features together all at once effectively. Now, within that, I also want to take a bigger picture view and kind of introduce this notion that like Mercury has a full hierarchy. At the bottom, you have individually programmatically generated features that get all built together through this next level in the hierarchy, which is feature groups. And then we have an additional notion, which is something we call a feature family, which is this idea that if you're counting, let's say, the add to carts across different geographies, well, you probably want the orders too, and maybe the times a product has been favorited. So that higher level in the hierarchy is a tool that helps with discovery and also helps with users basically being able to understand what features they want to use. So with that, I want to briefly summarize where this approach has taken us. The emphasis is on helping users define and maintain thousands of features and to do scoring for millions of entities every day. This enables us to run hundreds of models on Mercury in production. The real focus, however, is kind of these user experience improvements. So some numbers, rough numbers to share. A few systems migrated over from previous pipelines onto Mercury. When they did so, they observed, let's say, a few percent improvement in their target predictive metrics. For net new development, when teams started working on completely new projects, they reported sometimes reductions of 2 to 5 times in terms of time it takes to develop a new model. And one team reported saving up to 4 hours a week on the pipelines that they got to deprecate as a result of switching over to a centralized product. So with that kind of out of the way, I want to talk about focus in further detail on some of the key architectural enablers behind Mercury. I won't go into everything, but rather I want to focus on the kind of key enablers of this mission to define and produce many features efficiently. I'll focus on what I call the paved path. It's shown here with these kind of purple boxes. So raw events get pre-aggregated. From those pre-aggregations, features are built as grouped and consumed across scoring, most often through Spark ML libraries. And there are going to be 4 key lessons I want to share from that paved path, which I want to highlight because I think they're generally applicable, regardless of whether your feature processing system is going to look like Mercury or potentially look quite different. So they're about the importance of pre-aggregation, about the ability to package features together as vectors, an emphasis on reproducibility, and different ways we can drive feature reuse. So first of all, I want to talk about pre-processing. So you probably know that if you want to compute an average over some set of events or some set of facts in your data store, you don't need every single event, every single row of some table. You just need kind of sums and totals. So you can pre-aggregate data and kind of boil it down into just what needs to get used later. So here's a made-up example. We have some made-up products and the price of those products in various orders and across various geographies. So rather than computing averages by directly scanning through all of this, what we do is store sums and totals. And when it comes time to computing features from this, we have a lot less work to do. Similarly, the process is also helpful if you want to enrich data. Say if you want to, rather than grouping by geo, you want to group by, let's say, style. And maybe to count the style of products that a customer is buying. Well, if the style of the product isn't in the event itself, you can just join ahead of time to save yourself having to do it later, but still create essentially the same core data structure. And we found significant savings by having systems pushing compute earlier into the pre-processing to make future downstream compute run faster. So despite being very opinionated about this data format, the approach actually supports many different types of features, averages, extremas, sums, counts, so forth, right? Probably more that I haven't listed here. It doesn't support everything. You can't easily count distinct values, and there are some complex sequence processing things that obviously are a little bit harder to do, but nonetheless, like some of those calculations can be approximated pretty well through these approaches. And furthermore, you can choose to aggregate over different types of windows. I know lots of feature processing systems do this, but here I'll just say we kind of have two things are enough for us. We have, for features that have up to a 1-year look-back window, we use daily binning or things smaller than that. And for things beyond that, we can combine both daily and monthly aggregations. Okay. So now, given those aggregates I've shown you, I want to talk about how Mercury builds features and from those aggregates in groups and packages them as a vector. So busy slide, I'll walk you through it. But the goal is to have a quick picture of what this looks like. And we're going to make a group of features that all at once, for both average price and total orders per a supplier. And we get that across various geographies and across various time windows. So at the very top on the left, the user provides a list of entities for which they want to calculate the features. So this is, in this case, suppliers, dates. From that user provided list, Mercury actually builds an entity mapping layer. So it maps suppliers to products because the data that we need to build this feature is aggregated at the product level. And then the mapping data is joined to pre-aggregated data. That's this top table on the right. Along the way, you group on things or aggregate on things like the time window, the geography, the supplier, and then you do the aggregation that allows you to compute values. Now, once all of that's done, all of your features each feature is basically a different row for, let's say, a fixed supplier here. What we do is we pivot back into a single vector for the entity. And this actually deploys all the features and produces them all at once while actually needing to do only a single scan of the large underlying data. Okay, so these large vectors may seem like they're kind of bulky and difficult to use, but we've actually found they can be used quite flexibly and easily, particularly in Spark ML. So I want to just give an example of this. So here we have 2 of these feature groups. We can, one of them has the numbers you can see in red, one has them in blue. What you can do is concatenate them together. So this builds you a single vector. And then you can have multiple models who are packaged together with what is in SparkML, something called a vector slicer. This allows them to essentially pick out from this vector only the features that a model needs. And this packaging actually makes it possible for lots of models to share the same vectors while not having to actually use all of those features. And it simplifies the operational process so that you can run, many, many models that are all sharing the same data set. So the next lesson of these 4, this is now number 3, that I want to share is about how the choice of upstream data sources influences the requirements of feature processing. To explain this point, I have to introduce a tiny bit of terminology. And the reason is I think feature store can sometimes be a little overloaded. I think it helps to break down the functionality into 4 key parts. So there's a library, that's the collection of recipes by which you make features. That could be SQL, could be a YAML file, could be a collection of Python functions. Then you have an engine, which is how those recipes get materialized into values. That could be streaming, could be batch, could be some combination thereof. You have archival, which is the ability to store outputs of feature computation for further use. And of course, you can also cache for low latency retrieval. Sometimes when you're building features from data sources where you can't reproduce past state, in those cases, the information might be getting overwritten, or you don't know when it got written into the source at all. In these cases, you can turn to feature archival to give you a measure of online-offline consistency. But this still has some drawbacks, right? You might need months of historical data to train a model, particularly if the events you're trying to study or trying to model are rare events. You might need to look back for a very long time those. Also, when you cold start and build a new feature, you have some period where you need to accumulate new features for training. Now, on the other hand, if the data source you started with has an easily reproducible historical state, so like maybe it's an append-only log that replicates the data that was being streamed in real time, and all of the timestamps are properly, provided, then you can design a feature engine and feature library around that fact, and produce and reproduce features quite reliably in practice. Excuse me. And this actually diminishes the need for feature value archival and helps you save quite a bit of money on storage costs in our case. So, so the 4th lesson I want to talk about is different mechanisms that we found from this architecture on driving feature reuse. So we spend a lot of human and machine time writing, calculating features. We should want to make sure that those features get used. Earlier, I mentioned how feature vectors can be sliced and consumed by multiple models, particularly in SparkML. I've also talked about how Mercury reuses pipelines to build features together. Now I want to talk about a different kind of reuse, which is the reuse of a feature definition across multiple entities when building features. Let's start with another example. So on the left, you have data that is pre-aggregated at this product date level. In a previous example, I showed you can group these products by supplier and use that to compute feature values. However, it turns out if you hadn't grouped on supplier and instead you were grouping on product class, well, all of the subsequent recipes downstream, all of the subsequent steps in the recipe downstream would have been exactly the same. Similarly, if you had kept the data at product level, you could also do all of the subsequent, after grouping at product level, all of the downstream steps for calculating the features would be exactly the same. So this is a remarkably powerful idea. It means you could write 100 features for one entity. So let's say you could write features at the option combination level. That would be something like, how often has this particular red king-sized bed frame been purchased? And then you could actually reuse that feature at the next level in the hierarchy, which is how often has this bed been purchased for all different colors and all different sizes. You might even be able to reuse the feature at category level. So like, how many beds have been purchased, right? These values that you're computing are different, but the single recipe can actually be reused. And this pattern can actually be reused in many places because there are many places where you have hierarchies of entities like the ones I'm showing you here, whether that's in ad campaign management, whether that's user accounts belonging to different businesses, so forth. So that's an often kind of unusual form of reuse. I think there are other drivers of reuse I want to kind of highlight quickly. So first, I think it's important, or I think it's helpful that we have leverage from being able to produce many features with fewer lines of code. You can read all the feature definitions your model uses, and this actually reduces the need for some forms of metadata management. Second, I want to highlight that discovering features by metadata alone, such as who uses them, who owns them, when were they created, is often secondary to just being able to know whether the feature will improve the model performance for the problem that you're working on. And for this reason, just as the earlier speakers from Uber alluded, we've invested in automated and scalable feature selection methods so that you can traverse these large feature libraries to find features that are helpful to your problem, not just on metadata alone. And last, I want to point out that in my experience, the single most effective way to actually get ML teams to reuse each other's features is about having clear expectations around what happens in the event of changes to upstream data, who's going to be making changes to the definitions, who's going to be having to retrain, and so forth. And combined, I just want to share all of these because I think all of these are incremental parts in scaling reuse and therefore scaling the number of features that each team can effectively use because they don't have to keep their own copies. So with that, I just want to provide a little bit of intuition for why Mercury has been effective in making models performant. Making lots of features like this doesn't seem at first like it's guaranteed to work well. But I want to put the results in the context of some previous theoretical results about something called random kitchen sinks. This isn't a proof, but it's a helpful vehicle to build intuition. So to do this, the intuition depends on the following analogy. Think of your enterprise data lake as a kind of neural network, right? Let's think, so on the left, we have a neural network. It takes inputs on the left, I1, I2. Through linear algebra and some nonlinear functions, you get the numbers in the middle, H1 to H5. Those then get consumed to build the output O1. A common way that we build intuition about the functioning of this network is to think about the middle layer, H1 to H5, as kind of building features from the raw data, right? And because the model trains over time and learns better weights, you can think of the network actually iterates to build better features. Okay, so then now on the left, let's look at the data ecosystem. A very simplified picture is you have raw data, perhaps in the form of some event logs. You write features to transform the raw data via some functions, and then you combine those into a model. Over time, your data engineers, ML engineers, data scientists tune the feature definitions to make the features better. Now, that brings me to this paper by Ali Rahimi and Ben Recht. In the interest of time, I'm going to try to distill the paper through these two pictures. On the left, if you visualize what's happening in the training process of a neural network, you have these hidden layer, these values H1 to H5. They depend on I1 and I2. And in the plot, what we're basically showing through these colored marks is how much each one depends on I1 and I2. Now, let's say there's a best case performance where these 5 hidden units, these things, their dependence on I1 and I2 is represented by the black stars. So the goal of training the network is so that over time, these colored marks move around to be on top of those black stars. And that's what happens when you train a conventional neural network. Now, what this paper shows you is that instead of doing that on the left, what you can do is on the right. Rather than trying to tune the featurization process, you just initialize many, many features at random and apply a simple learning procedure to figure out how much to weight them. In fact, by using an L1 penalty, you can use sparsity to basically throw some of them away. And what this paper does is it uses functional analysis to basically prove the models you get are very similar with high probability, but there's this further benefit that they train up to 10 times faster. So to further distill this down, the key idea here is you want to replace a slow end-to-end learning process with a fast, high-dimensional kickstart, and then you want to quickly learn how to do weighting. So if we translate that to the enterprise data warehouse, what I'm saying is you can take 2 approaches, right? You can iterate to build 5 perfect features, or you can make many features and learn to weight them well. Essentially, what I want to suggest is that programmatic feature generation gives you this on the right of this inset. It's a not so random kitchen sink. It's a large basis of features in a complex functional space that's hopefully very close to the best case you would have if you tuned your features by hand. And in practice, because we have finite time to train models, the models you get out of this are actually quite performant. Now, I want to be clear, I'm not saying feature quality doesn't matter. Features should all be of a high standard. But what my message is that you want to maximize the value delivered by a portfolio of all features and over all of the models that consume them. It's hard to know in advance which ones are important, so it helps to have a large library of high quality features to draw on. So lastly, I just want to situate this in what I think is a growing trend. Over the last decade, there's been a considerable investment in so-called AutoML frameworks that take a given data set, optimize training over that data by handling things like hyperparameter search and missing data imputation. The methods are very powerful. They've saved a lot of human effort. They've become the basis of offerings at many cloud providers. But these methods only work with the data that's been given to them. And where I think there are still opportunities is about extracting more data from the warehouse, from what's available, and making it easily consumable. The area is much less mature, but I'm happy to share some of our first forays into this problem space. And I'm excited about what future changes are going to look like. So thanks. And with that, happy to take any questions.
Thanks a million, Alexander. That was a tour de force, I think.